Hello everyone, welcome to my channel. This is an educational channel, and we try to look at various theories of everything, cosmologies that purport to describe our universe that we live in, and everything about it. And we look at usually at cosmologies that are not well known, and maybe not the easiest to break down, but some that are things that you would benefit from if you were exposed to them. And today is, I believe, the 328th or 328th video that we've done on Dewey B. Larson's reciprocal system of theory. Dewey B. Larson lived in the 20th century, and he came up with what he called the universe of motion. And this was his idea that the universe was made out of motion. Not matter, not energy, but motion. And for Larson, motion was the relationship between space and time. And in the late 1950s, he came out with his two fundamental postulates that outlined this universe of motion. And from there, he took those two postulates, and through a process of deduction, he came up with his theoretical universe. What his universe would look like if the postulates were true. And then he compared his theoretical universe with the observed and measured universe of the legacy scientists, and described their coincidences and their oppositions. And I believe he made a great contribution, but nobody knows about it, and there are very few people who have studied up on the reciprocal system. Larson didn't make it easy. It's not an easy subject to start with. But Larson was generally trying to address a scientific audience, and I don't know, he didn't necessarily understand that the scientists were actually the last people in the room who were going to get it, because they were the most wedded to the paradigm, the current paradigm that you know, of this universe of matter or universe of energy or whatever. And so they were going to be kind of the least open to accepting his theory or even taking it seriously. Whereas maybe other audiences, had he written in a way that would have been more accessible to other audiences, he might have had better results. But he put the information out there, but it's just kind of hard to retrieve. And so that's hopefully where I come in. I'm not an expert on the reciprocal system, but I have read pretty much all of Larson's work, books anyway, and most of the articles. And you know, I'm trying to you know, go through his work with the fine-tooth comb, and you know, just present it, but also to a certain extent, like, you know, be a guide or hold your hand, and you know, help you to access this information as well, so that you can make an informed choice, as opposed to just, you know, rejecting it out of hand or not ever knowing about it or anything like that. So what we're doing today is we're looking at Larson's article that is called "The Nature of Motion." And so he's going through kind of explaining his universe of motion by first pointing out that the legacy science throughout its history, going all the way back to Newton, has never really defined motion properly. Newton basically just assumed that everybody understood motion. that being known to all, I believe is what he said. And but Larson is pointing out that there's a kind of motion that really differs from the normal motion that we're accustomed to, that is a scientific fact, but it hasn't really been investigated by science, and that's what he calls scalar motion. And a scalar motion is a motion that has a magnitude, but it has no specific direction. Most of the motion that we define is a vector. It's a motion in a direction. It is a velocity or something to that effect, that it has a magnitude and a direction. But a scalar motion just has a magnitude. And you can see scalar motions in the real world. The Hubble telescope has identified that all of the distant galaxies are moving away from each other. And unless you are, as Larson pointed out, unless you are prepared to say that our galaxy is at the center and it's the only one that's not moving, then otherwise you would have to assume that our galaxy is participating in this same motion, that our galaxy is also moving away from all the other galaxies. You would represent this kind of motion using a balloon and dots on the balloon. If you blow up the balloon, all of the dots are moving away from each other, but they're not moving in any specific direction. And so that is a scalar motion. But that motion differs in kind to the general motions that are reckoned by scientific inquiry. And nobody has investigated scalar motions to the point where they need to. And he's also identifying gravity as being a scalar motion really moving in the opposite direction, just like spots on a balloon, but you're sucking in the balloon. So all the spots are moving toward each other. And normally science says that gravity is an attraction between two bodies, and there's some kind of force between those two bodies. But Larson is saying that, well, no, that's only if you give one of those forces, one of those points, one of those locations, and you call that the reference point, and that's the point that's not moving. If you couple that balloon to a reference system, then it does appear as if two bodies are attracting one another. But actually, it's really that all points are moving toward all other points. It's just that you haven't identified these other points, and you've identified one as the motionless reference point. So it's really misleading to view gravitation as being this kind of force object at a distance, being attracted by some kind of so-called force field. It's really just the contraction of space itself. So Larson is really saying the space itself is what is moving. And so everything that is in space, represented in this analogy by the surface of the balloon, everything is moving toward everything else. But we just see it as one toward another because we've identified a reference point. Okay, now this is now Larson's postulates get into various other things, and I've gone over those in really every video that we've done on the reciprocal system, and he probably will go over those things in this article as well. This is the third installment of this article, so if you want to go back to the beginning, you want to go back 2 videos and watch those 2 previous videos. So I'm starting here in the middle of this article, but he just got done talking about, kind of what I'm saying, that I'll just read the last sentence here. This obstacle is now removed by the finding that all gravitating objects are moving inward in all directions, and that the apparent lack of motion in some cases is due to the inability of the reference system to represent scalar motion as it actually exists. Ordinarily, motion of a mass is produced by the application of a force. The observation that mass B in the vicinity of another mass A acquires a motion toward A, while mass A acquires a motion toward B, has therefore led to the conclusion that each mass is exerting a force on the other. However, our discussion thus far has dealt only with motions. In order to clarify the role of force in the gravitational process, we will need to consider the relation between force and motion. For application in physics, force is defined by Newton's second law of motion. It is the product of mass and acceleration, F equals ma. Motion is measured on an individual mass basis as velocity. That is, each mass unit moves at this rate, or also on a collective basis as momentum, the product of mass and velocity. Momentum was formerly called quantity of motion, a term that more clearly expresses the nature of this quantity, which is actually the sum of the motions of the individual units. The time rate of change of the motion is dv over dt, acceleration A, in the case of the individual unit, and in dv over dt, force, or ma, when measured collectively. Thus, force is a property of motion in exactly the same sense as acceleration. It is the time rate of change of the total quantity of motion, the quantity of acceleration, we could appropriately call it. The significance of this point in the present connection is that a force cannot be autonomous. By definition, it is a property of motion. Thus, wherever we find that a force exists, it follows that there must necessarily be an underlying motion of which the force is a property. This is a positive requirement with no exceptions. A force cannot originate in a motionless object. Either the object itself or one or more of its constituents must be moving in the direction of the force. There cannot be any such thing as a fundamental force. The so-called fundamental forces are the force aspects of fundamental motions. In the gravitational case, we have found that all members of any system of gravitating objects are moving toward each other, even if one of them is represented as stationary in the reference system. The gravitational force is the force aspect of this gravitational motion. Since scalar motion takes place coincidentally in all directions, the magnitude of the mutual gravitational motion of two masses is distributed over the area of a spherical surface with a radius equal to the distance between the masses. The gravitational effect thus varies inversely as the second power of the distance. Where this distance is large in proportion to the amount of mass involved, the effect is negligible. But at the shorter distances, each of the constituent units of mass A has an inward gravitational motion toward each of the constituent units of mass B. If both masses are free to move, the representation of the mutual motion in the reference system is divided equally between motion of A and motion of B. If the location of one of these masses is represented as fixed, the entire motion is attributed to the other mass for reasons explained earlier. It should be noted, however, that the reference system does not represent the total scalar motion, the product of speed and the number of units involved. It represents the speed only. Thus, the motion measured as speed of mass B is represented in the reference system as proportional to the total motion AB divided by the mass B. That is, it is proportional to the mass A. Here then is the explanation of the gravitational field. The question as to the nature of a field is a long-standing scientific problem. A typical definition taken from a physics text says that an electric field is, quote, what is in the space around an electric charge that allows one charge to interact with another, end quote. As this definition indicates, a field, the field, is a phantom. There is no actual evidence that there is anything in this space that could be identified with the hypothetical field. But the currently accepted physical theories require some kind of a medium to transmit gravitational and electromagnetic effects. It is therefore assumed that there must be something in the space that serves this purpose. For the modern physicist, says Einstein, the field is, quote, as real as the chair on which he sits. In fact, the only way in which any indication of a gravitational effect in the vicinity of a massive object can be obtained is to introduce a test mass into this space. This test mass accelerates toward the massive object. But as brought out in the foregoing discussion, this is not due to anything that exists in the space. Each mass has an inherent scalar motion that carries it toward the other, carries it inward toward the other. As has been explained, the scalar speed of mass B toward mass A is independent of the mass of B. It is determined by the magnitude of the mass A and the distance between the masses. Thus, each point in the space surrounding mass A can be characterized by a magnitude representing the gravitational speed that a mass would have if it were located at that point. However, the actual speed of such a mass always includes an additional component of a vectorial nature, unless the mass has been in free fall all the way from a great distance. It is therefore convenient to take a different property of the motion, the force or the total acceleration, rather than the speed, as the acceleration is a result of the geometry of the scalar motion and is independent of the accompanying vectorial motion. Each of the spatial locations surrounding mass A can be assigned a magnitude and a direction, representing the gravitational force that would be exerted on a unit mass if one were present. The ensemble of all of those vectors is the gravitational field of mass A. We thus see that the field is not a tangible physical entity. It might be compared to a set of steam tables. We can refer to these tables and determine the heat content of the steam in a boiler at specific certain levels of temperature and pressure. But this does not tell us anything about the conditions that actually exist in the boiler. It may not even contain any steam. The tables merely tell us what the heat content would be if certain conditions did exist. Similarly, the tabulations of field strength tell us only what forces would be experienced at specific locations if masses happen to occupy those locations. The force field has no more physical existence than the steam tables. The foregoing explanation of the origin of the forces that appear to be exerted on distant objects is also, the foregoing explanation of the origin of the forces that appear to be exerted on distant objects also provides the answer to the long-standing problem of action at a distance. Newton's gravitational law appears to call for direct action of one mass on another, regardless of their spatial separation. But many scientists are strongly opposed to the idea that a force can be exerted without a physical contact of some kind. The prevailing opinion has therefore been that the force must be transmitted through some kind of a medium, notwithstanding the total lack of evidence to support such an assumption. The need for this hypothetical medium is now eliminated by the finding that each object in a gravitational system has an inherent negative or inward scalar motion and is therefore approaching all other objects in the system because they are moving inward in the same manner. When the gravitational situation is thus clarified, it becomes evident that the forces due to electric charges and the corresponding magnetostatic phenomena, magnetic charges we may call them, are likewise properties of hitherto unrecognized scalar motions. Observationally, these motions differ from the gravitational motion only in those respects in which scalar motion in general is variable. That is, the motions may differ in magnitude. They may be either positive or negative, and the nature of the coupling to the reference system may vary. Here again, the absence of observable motion at the point of origin of the force is due to the fact that the location of the charge is the reference point, at which the representation of the motion in the reference system is frozen by the coupling of the moving scalar system to the fixed reference system. Okay, I think we're going to stop right there, and we'll do one more paragraph. The existence of these different types of scalar motion raises the question as to why the apparent interactions are limited to motions of the same kind. why electric charges interact or appear to interact only with electric charges, and so on. The answer can be found in the mutual nature of scalar motion. Since the motion of A relative to B and the motion of B relative to A are merely two ways of representing the same motion in the reference system, it follows that a scalar motion AB cannot take place unless the individual motions of A and B are of the same scalar type. There is no interaction between a charge and a mass. Okay, might revisit that last paragraph to start tomorrow, but otherwise we're going to leave it there. Now I know that if you're just tuning in here, you're a little bit confused about the reciprocal system in general, but let me just give you a quick once-over here. Larson saying that the universe is made out of motion, specifically scalar motion, and that motion in Larson's system is the relationship between space and time, and that time and space are basically non-existent, except they do not exist separately. They only exist together in motion. Motion is basically a fraction with time or space as the numerator and space or time as the denominator. This sets up a generalized reciprocal relationship between space and time, hence the name the reciprocal system of theory. And so time and space are basically identical, except that they are reciprocals of one another. And they both have the same qualities. And Larson lays this out in his first postulate. Space and time are both coordinate, meaning that they both come in 3 dimensions, or they both have aspects that are 3-dimensional. Space and time are both progressing, or what he calls clock time and clock space. The clock is progressing. Time is always getting later and later and later and later, but in no specific direction, like a scalar motion. Space, too, is progressing. Space is always getting farther and farther and farther apart, like 2 dots on an expanding balloon. But they're not getting farther apart in any specific direction, a scalar motion. And then space and time also are quantized, meaning that they come only in discrete units. There is a minimum unit of time, and if you don't have that full minimum unit, you don't have time. And there is a minimum unit of space. If you don't have that full unit of space, then you don't have space. You have to have a full unit before you have either of those qualities. And if you have exactly 1 unit of space in 1 unit of time, you have the speed of light. So in Larson's system, a universe of motion, the speed of light is the fundamental speed, the speed of light outward in all directions in a scalar manner. And that contradicts the legacy science, which basically says that they make all their measurements from zero speed. Larson makes his measurements from unit speed, what he calls unit speed, or the speed of light outward in all directions. So in the universe of motion, the natural state of rest, what Larson calls the natural reference system, or you can think of it as an origin or an ether or a 0 point state of rest, is outward at the speed of light. And so that is really the main paradigm shift difference, is that we have a moving reference system. And another paradigm shifting change is just that for 3,000 years, we have been accustomed to thinking of space and time as being the container of the universe. It's really like the stage upon which all of the actions of the universe take place. But in Larson's system, space and time themselves are not the container of the universe, they are the contents of the universe. That is what the universe is made out of. And not only the stage, but also the characters on the stage are made out of space and time. So that maybe will just give you a round out of the reciprocal system, and we'll get into this the fourth installment of this paper, The Nature of Motion, in the next time out. But just, the main point is that now that we understand scalar motion, we can kind of throw away some of these assumed concepts of modern science, so-called modern science, that there has to be action at a distance, and that gravitational, magnetic, and electric forces are between two specific objects. It's not that what we're doing is we're misplacing the origin of these motions. The motions themselves are because space itself is moving, and everything that is in space is moving, either away from or toward each other. There's not a force between them. The motion is coming from the space itself. Okay. Thanks for tuning in today, and have a great day. Hope to see you tomorrow.